Hey everyone, welcome back to physics. This will be lecture 26 of the course. And in this section, we're going to discuss a kind of an add-on topic to work, and that is the concept of power. So let's go ahead and jump into it. We'll call this section 5.3 power. So when we recently discussed work, i.e. the last two lectures, we saw that in our definitions of work, time was not referenced. So we saw that work was equal to the dot product of force and displacement. You can think of that as vectors. In the case of forces that are variable, we use the integral x initial to x final of force relative force ds, right? So we saw this kind of a definition also. And we saw a couple others that sort of broke down the dot product using trig functions. But in none of the definitions did we see time referenced. We did not see time referenced in our previous work definitions. Okay, and so the idea here is that, well, if that's the case, then apparently time is irrelevant when it comes to the quantity that we call work. So if I have a 1,000 Newton weight that I move 5 meters, the same amount of work is done if it takes 1 minute or if it takes 1 month. So the work is the same if this task takes 1 minute or 1 month. Okay. So, I mean, on the surface, we definitely, when it comes to you and I as beings that do work, there certainly seems to be a difference between moving 1,000 newtons over 5 meters in a minute versus moving 1,000 newtons 5 meters in a month, right? So there is certainly some kind of difference there. But in terms of work, it's the same, right? Work is just a force over a displacement, right? So if we want to introduce the idea of the kind of the rate at which work is done, then that is the concept of power. Power. Okay, and so what is power? Well, we'll start with the idea of average power. Average power. This is, just denoted with a P, and then we'll put an average subscript down here. And average power is the change in work divided by the change in time. So it's the amount of work done over an interval of time, right? So basically a work per unit time. That's average power, right? And then, of course, there's instantaneous power, which would be just denoted as P, and this is going to be the limit concept. So we're going to take the limit as delta T goes to 0 of this average power. And when we do that, of course, we get dW dt. So the derivative of work with respect to time is power. Okay. Now, what are the units here? Well, the units are, what's work? Well, work is joules, or we can say Newton meters, and then work is, and then time, of course, is seconds. All right, so Newton meters per second, or you could say joules per second. And we have a name for that. It's called the watt. A watt of power, just denoted with a W, right? So you've certainly heard of watts when it comes to electrical, electricity and such, but it has a more general meaning in physics. It's a measure of power. And then we'll talk about, in the British system, we have things called pound-feet per second, and a concept called horsepower, which we'll get into in a little bit in an example. But the sort of SI unit here is the watt, which is just joules per second. Okay, so power describes how quickly work is done, or another way to think about it, power is the rate of change of work with respect to time. So power is the rate of change of work with respect to time, right? So dW dt. Okay. All right. So that's really the idea. Let's go ahead and work an example quick. So this will be kind of a shorter lecture. It's kind of an add-on topic. Let's do an example though of power. Okay. So our example is going to involve an athlete running up the stairs of a very tall building. So we'll say an athlete with a mass of 50 kilograms runs up the stairs to the top of a 443 meter building. So runs up the stairs to the top of a 443 meter tall building. Okay, and I believe this is like the Sears Tower. It's very tall, right? So one of the taller buildings in the world. And we'll say that she does this in 15 minutes, which is 900 seconds for those of you wondering. So if you can run up, if you weigh 50 kilograms and you run up the stairs, you run up 443 meters of stairs in 15 minutes or 900 seconds, question is, what is her average power output in watts? What is her average power output in watts? And then we'll, just for fun, we'll do kilowatts as well, and horsepower, right? So horsepower is like the British equivalent of like kilowatts, basically. Okay, very good. All right, so simple enough, right? In theory, you've got these stairs, right? And since this is like the Sears Tower or something, they kind of go back and forth, right? And so you're running up these stairs, up a flight, and then you go up, and then you go up another flight here, and then you go up another flight here. So you're zooming up these stairs, right? And we'll just ignore the work done in the horizontal direction. This is sort of an approximation. We're just interested in the vertical work, which is by far the larger piece of it. So, all right, very good. So how do we want to solve this problem? Well, we're going to think of the athlete as a point mass. We'll think of the athlete as a point mass, right? And with a weight that we can easily calculate. So we'll think of the athlete as a point mass with weight. Well, W equals mg, which in this case is 50 kilograms times 9.8 meters per second squared. And so you'll see that this athlete's weight is about 490 newtons. Okay. Now, you've got this weight moving up these stairs. So what is the work here, right? So let's think of the free body diagram. You've got this, just in the vertical direction, you've got basically 490 Newton weight, and you've got a normal force on the stairs. Now, in order for the runner to move against gravity, there has to be an additional force exerted that overcomes this normal force, right? And so the work done here is essentially moving this weight, 490 newtons, against gravity up the tower height of 440 meters. So basically, the force is the force of moving up a single step, right? So the work here then is mg times the height of the tower. That's the displacement. Right? So this would be like your force. This is your displacement. Okay. And so what are these quantities? Well, you've got 490 newtons. That's the force exerted. And you've got a displacement of vertically 443 meters. Okay. So this is gonna tell you specifically the work required to go up 443 meters. There is, of course, a horizontal component to the motion, but we're not interested in that part. That's not part of the displacement that we're interested in. We're interested in the vertical displacement of 443 meters. Okay. And so when you multiply these two together, you get 217,070 joules. So this is the amount of work done in moving this athlete's body up 443 meters. Okay, so this is the work. So then the question is about power, though. The question isn't specifically concerned about, well, how much work is it? It's really more like, well, we did all this work in a certain amount of time. What's the power required to do that? Okay, so what's the power? So the average power is what we'll be interested in here. Right? The average power, the P average, is equal to the change in work divided by the change in time. And so we saw that this was 217,070 joules. This whole, all of this work was done in 15 minutes, which 15 times 60 gives you 900 seconds. Okay, so if you divide that down, you get 241.19 joules per second, otherwise known as 241.19 watts. All right, so that's the power required to move this athlete to the top of this skyscraper. Okay, in watts. Now, what about in kilowatts? What's the kilowatts? Well, it's just a conversion, right? So 241.19 watts. We want to convert that to kilowatts. Well, how many watts in a kilowatt? 1,000. Okay, you do the math there, divide it down a little bit. You get 0.02411 kilowatts. So about 2.5% of a kilowatt. All right. What about horsepower? Well, horsepower, what is horsepower? Certainly have heard this term, right? If you're a physics person or an engineer, you definitely have heard of the concept of horsepower. What is horsepower? Well, a watt is joules per second, right? In the British system, we don't have joules, we have foot-pounds or pound-feet. So in the British system or the imperial system, we don't have joules, we have pound-feet, foot-pounds, however you want to say it, pound-feet or foot-pounds. Okay, and so work in the British equivalent is in foot-pounds, right? And so instead of joules per second, we would have foot-pounds per second. That's power in the British system. Okay, and then a horsepower is a certain amount of power, right? So kind of like in the British system, you have feet, and then you just like jump up to yards, and you jump up to miles, and so foot-pounds per second is a measure of power in the British system, and then horsepower is just an aggregation, right? So 1 horsepower is equal to 550 pound-feet per second. Okay, right, and so that's what a horsepower is. It's a unit of power specifically equal to 550 foot-pounds per second. Right, so if you've got 1,000 horsepower, you've got 1,000 times this 550. Okay, so that's what a horsepower is, and you can do the math and like kind of do the conversion between pound feet and joules and blah blah blah. But what you'll find out is that 1 horsepower is equal to 746 watts. Okay, so that's the conversion. Right, so if we have this athlete's average power in watts, we can convert it to horsepower. Right, so we had that the power in watts was 241.19 watts. If I want to convert that over to horsepower, right, I can use this right here. And so I've got 1 horsepower, 746 watts. So I apparently need to do a division here. And you see that this is equal to 0.323 horsepower. That's the average power needed to move this athlete up the stairs at this rate. Okay, so 443 meters in 15 minutes requires average power of 0.323 horsepower. So about 1/3 of a horsepower. All right. Very good. So that's the idea of power. It's work done in some amount of time. Right? So it just brings the idea of a rate of work together. Okay. So that's where we'll end this lecture. And so the next lecture, we're going to do problems and examples. We'll see more examples of power and also of work and kinetic energy and the work energy theorem. Okay. So until then, take care.